Hey Bioteam, what this video does a deep dive into is how organisms keep themselves from making too much or too little of the products that they need. That is, how do they go about regulating their enzymes' activity? And so there's a couple of tools that cells can use. They can, if they want to speed up a reaction, use an activator, which is any type of molecule that speeds up or starts a process. Or if they want to slow down a reaction, they can use something called an inhibitor. So let's talk about inhibitors first. There's two types of inhibitors. The first type of inhibitor is a competitive inhibitor, which is a molecule that competes with the substrate for the active site of an enzyme. So we'll show an example of this here. We've got our enzyme and a couple of substrates that the enzyme would try to break down. The competitive inhibitor would have a similar shape to the substrate and have the ability then to temporarily block the enzyme's active site. So the idea here is that the substrate and inhibitor are in competition. Either the inhibitor or the substrate can win and interact with the active site of the enzyme. And so if the substrate's concentration is increased to a point where it can outcompete the inhibitor, the enzyme can still reach the maximum reaction rate. So in this example, this enzyme will still likely be breaking down substrate at close to the enzyme's maximum speed because there's just so much substrate available and so little of the inhibitor. But the opposite type of inhibition is called non-competitive inhibition with non-competitive inhibitors. And non-competitive inhibitors are molecules that denature the enzyme to the point where it can't break down the substrate. And so we've got an example of this here. We've got an enzyme before it's been inhibited, where it has an active site that's capable of binding with the substrate molecule. But after inhibition has occurred, after this little red inhibitor here has bonded with the enzyme, you can see that the active site of the enzyme has become denatured. In this case, it's bulged out in a way that the enzyme can't interact with the substrate anymore. And so unlike before with competitive inhibition, if we were to add more substrate in this scenario, it wouldn't do any good. It wouldn't increase the rate of the enzyme's reaction because the enzyme is just denatured. And until this inhibitor gets removed, the enzyme's active site would remain denatured. And so we call this type of inhibition where the inhibitor binds to a non-active site on the enzyme, we call that allosteric inhibition. And we call this inhibition up top, the competitive inhibition, we call that orthosteric inhibition, where the inhibitor binds directly to the enzyme's active site. Now, one of the places that these inhibitors can come from, either competitive or non-competitive, is through something called inhibition feedback loop, which occur when the products of a reaction become inhibitors of the enzyme and stop it from continuing to function. And so we'll show an example of that here. Here we've got an enzyme and a substrate, and the enzyme converts the substrate into an end product, represented here. In the case of feedback inhibition, this end product then gets fed back to the enzyme that made it, and in this case serves as an inhibitor. You can see that it's denatured the active site of the enzyme. And so at this point then, the enzyme's active site can no longer interact with the substrate. And so the enzyme has made a product that inhibits itself. As for why an enzyme would do this, this self-inhibition ensures that only a certain amount of the product gets made, or that not all of the substrate gets used up. It can be used for other things. So all of this is forms of inhibition, of slowing down the rate of an enzyme's reaction. Activation of enzymes is the opposite. That's what a cell would do if it wanted to speed up a reaction. And activation of enzymes works a little bit simpler. Activation can involve cofactors, which are molecules that can bind to an enzyme and open up its active site. So here you can see before this cofactor binds onto the enzyme's active site was closed off to the substrate. It wasn't able to interact with the substrate. But when the cofactor attaches to the enzyme, it kind of pops open the active site here and allows the substrate to interact. And then the other type of activation that we'll cover is something called substrate cooperativity. And so substrate cooperativity occurs when a substrate binds to an active site on an enzyme and actually opens up a second active site for another substrate to bind on. And so you can see that here. It looks like this enzyme only has one single active site, room for a single substrate. But when this substrate adheres to the active site, it actually forces open a second active site on the enzyme, allowing a second substrate to interact. In the process, essentially doubling the rate at which this enzyme can interact with the substrate. And so that's it. At this point, you guys have some practice problems. We'll see you next class.